I hope all of us are doing fine. My name is Anes, and this is Anes Sciences and Mathematics TV channel. So, in our discussion today, we're going to look at the heat capacity of a monoatomic gas, and of course, this is going to be a derivation of the last discussion we had on the concept of internal energy. Therefore, we can have a representation of the heat capacity of a monoatomic gas from the representation that we had on internal energy. And as we said, this particular relationship is unique in a sense that for both the classical and the quantum behavior, they're going to give us the same result, which basically is going to be, from this specific perspective, the result is going to be agreeing with the equipartition theorem, and of course, which is going to give us a similarity that I'm going to mention as we go by. Now, in this case, we're going to consider the aspect of an internal energy, which is going to assist us derive the heat capacity as a fire said for a monoatomic, of course, a gas. Now I'm going to, of course, have a recall of the last discussion we had on the internal energy of an ideal monoatomic gas. And we had said that for us to find the partition function of this specific monoatomic gas that is containing a specific range of atoms, we're going to consider the, of course, the atomic translation partition function, which was given for indistinguishable particles, which were given in terms of Qn over n factorial. And then we had said that basically this is going to translate into a form of the de Broglie's wavelength, given in terms of raised to negative 3, and that's with the product of Vn all over n factorial given as such. So we have said that basically we are going to give the translational partition function in terms of the negative value of or the de Broglie's wavelength raised to negative, 3, and this is going to be given in terms of the product of that one together with volume. Now I'd say that if you consider any particles for this translational partition function, then we're going to include this specific component of the exponent of m given as such. And for, of course, indistinguishable particles like liquids and gases, then therefore we're going to include this aspect of n factorial given as such. So from this specific representation, then therefore we're going to come up with the concept of or have a relationship of this particular partition function with internal energy. And I'd say that therefore considering u as our internal energy, we had derived u and given it a value of, let's consider this, u and u are not giving it as a value of kBt squared. And of course, the second part gave us a partial derivative of Q with respect to temperature at constant volume given as such. So this basically was a value of our internal energy. And we would say that this specific part is going to be the initial state, whereby we're going to have this one given from the ground state. And therefore, we're going to consider this one to be a value of 0 and have this one given as such. So we said that therefore we're going to consider one aspect of this specific translation of course this specific partition function, which are going to be depending on temperature, and therefore this gave us a way of trying to describe this specific equation, whereby we say that we can consider this first case of this specific representation for the partition functions of indistinguishable particles, and of course do a substitution in this particular expression for the internal energy. So this one gave us the value of kBt into the partial derivative of the natural logarithm. So we're going to do a substitution here of this specific case by doing so. I can do away with this, of course. I'm going to put it as a reminder somewhere. So we're going to have this one as the partial derivative of the natural logarithm of Q. Now in this specific case, our Q is going to represent the values over the de Broglie's wavelength. And of course, if we consider a particle of n, of course any values, then therefore we're going to have this one as negative 3n. And of course, we're going to have this one together with the Vn all over n factorial. And this is going to be in terms, perhaps I can put it this way so that we are going to differentiate that over sign, or the division sign in that particular case. And all of this is going to be with respect to temperature, of course, under constant volume, as I had said. So basically, considering this specific partition function, we can represent an aspect of internal energy of this monoatomic ideal gas in terms of this particular representation. And of course, we're going to use the laws of logarithm in trying to evaluate this specific representation. And I'd said that we're going to also to take properties which are going to only to depend on temperature from this case. And of course, one of the properties that is going to depend on temperature from the de Broglie's representation, which is a wavelength, then therefore it's going to be this particular lambda. And I'd said that basically this lambda represents a value. So we're going to see how this one depends on temperature. It's going to depend on a value of kBt all over h, the square of h. And therefore we're going to have this one. So if you try to look at these various constants, and assuming that the mass of this particle is a constant, then therefore we're going to have a temperature as a variable. And of course, the lambda is going to depend on temperature in that particular case. So we're going to consider only this specific aspect of lambda, and we're going to assume the rest. So in this case, this specific expression, therefore, for internal energy is going to translate into a form which is a kBt, the square of that, and we're going to have this one as the partial derivative of the natural logarithm, of course, with respect to temperature. And this upper part for the energy is basically going to be given in terms of T, 3n over 2, and of course that is given as such. Considering those specific values that we have given for that, so the solving or the equation, this equation is going to give us a value of this one using various laws of logarithms. And of course, I'm not going to go into details of that. Now, in this case, from this particular case, we are also going to use the laws of logarithms. We can see the natural logarithm at this specific point. And for that, the treatment of natural logarithm with the exponent at this specific point, we're going to take this one come in front as a constant, and it's going to form some kind of course, a coefficient in that specific respect. So therefore, this is going to reduce into a form of 3n, which is a power. I've said, of course, according to laws of logarithm, this one is going to come in form of an exponent, and we're going to have k b t at the square of that, and of course, we're going to have this one. The natural log of this specific t with respect to this is going to give us 1 over t given as such, and of course, the value of u is going to reduce into a form of 3 over 2, and n. This is going to be nkb, and the value of t given as such. So this is a derivation of our internal energy having considered the partition function for this specific case for n particles, and doing a substitution for this is going to give us an evaluation of that specific energy. So this is going to be a representation of internal energy of that specific monoatomic ideal gas, considering any number of particles given as such. And therefore, from this specific formula, we have said that we can represent the heat capacity of a monoatomic gas from the derivation of this specific formula of internal energy. And of course, this result is going to be equivalent to the classical result which we are going to obtain. Now, using the relationship between the Boltzmann's constant and the universal gas constant, we can still find a relationship which is going to give us a final representation of this specific formula. And in this case, I've mentioned the Boltzmann constant and the universal gas constant. And this is going to give us a formula over n kb, NAKB. And if we try to look at this specific section of the formula, then therefore we can have internal energy over this monoatomic gas given in terms of 3 over 2 RT. And this is going to be, of course, a representation of the molar translation internal energy over that specific system under consideration, and therefore that's going to be a final part of this specific formula. Now, I mentioned that basically this specific result is in agreement with the equipartition theorem, and of course which is going to be either be in terms of given the same value either in terms of a classical or a quantum value in that particular order. So in this case, if we are going to look at this specific aspect of the heat capacity of monoatomic ideal gas, we're going to represent this heat capacity in terms of CV is equivalent to the partial derivative of this internal energy, or the partial derivative of this respective molar translation internal energy with respect to temperature. And of course, if we do a derivative of this specific value with respect to temperature at constant volume, we're going to obtain the value of 3 over R. So basically this is going to be 3 over 2 R. So a derivation of this with respect to temperature is going to give us this specific constant for 1. And of course, this is going to be given in terms of, so we said we can find a derivative of a number. So t is equivalent to t raised to power 1. And this, of course, is going to be a coefficient minus 1. So a number raised to 0 is equivalent to 1. And that's going to reduce into a formula of this specific nature. So therefore, representing the heat capacity of a monoatomic gas is going to be given as 3 over 2. So this is going to be 3 over 2r. And that's going to be the formula that we are going to be using in representing this specific aspect. So I hope we have understood from that particular perspective. And catch us in our next videos. We're going to look at other areas. So subscribe to our channel and engage us in the comment section, and also check our of course, a description box for a link of other similar videos. So that is it for now, guys. Bye, God bless.